Hello everyone, this is Mr. Ainsworth, and we're going to get into section 1.4 on continuity of a function here. And what we want to do, basically, in simple terms, is determine continuity at a point on an open interval. And to do that, we're going to be taking a close look at limits. We're going to evaluate functions at a point. We're going to be analyzing piecewise functions, and at the end we're going to also take a look at what's called the intermediate value theorem as well. Okay, so basically what we want to do first is to determine continuity at a point. What does it take to be continuous at a point? So what we're going to do first is take a look at three graphs and three situations where f of x was not continuous, or what we say is discontinuous at some point, and understand the qualities about them to basically determine what it takes to be continuous at a point. All right, so let's take a look at our first situation here. Let's take a look at a function with a hole in it. So let's say that f is here, and let's say that it's discontinuous at c because we have a hole there. And let's say that this right here is f of c. So there's a hole at c comma f of c. I'm going to ask you, or give you three different situations here. I'm going to ask you the same questions for each. And then afterwards, what we're going to do is we're going to figure out a way, basically a test, to determine continuity at a point. Okay, the first thing I want to ask you is, in this case, is if f of c is defined. And the answer in the first case is no, because there's a hole there. That indicates where the function's undefined. So the first thing is that we notice that in the first graph that f of c is not defined. Okay, at c is not defined. Why? Because there's a hole there, and the hole indicates that the function is not defined there. Question 2 is, does the limit exist? In fact, let me write the questions over here. And these are the questions that I'm going to be asking. First one, question 1 was, is f of c defined? Question 1, is f of c defined? Question 2, does the limit exist? Does the limit of f of x as x approaches c, does it exist? And then third question, does the limit of f as x approaches c, does it equal f of c? Okay, I'm going to ask you those three questions for each graph. Okay, so question 1, and because we have a hole there at c, the f of c is not defined. There's no value for there. It's not a real number. Okay, question 2, does the limit exist? Well, let's analyze that. Let's take a look at it. And we're coming in from the right here of c. We'll notice that the function values are increasing. They're getting bigger, and they're approaching f of c. So we said that the right-hand limit is f of c. If we're coming in from the left of c, the function values are decreasing to f of c. So the left-hand limit is also f of c. So in this case here, just like in the last section here, this function has a limit which is equal to f of c. So I'm going to put L there for limit. All right, so the limit exists in this case, and it's equal to L, or f of c. So limit of the function exists. Okay, and it's equal as x approaches c, and it's equal to f of c in this case, or L. And even though the function is discontinuous there, it's kind of funny, but the limit can't exist even though there's a discontinuity at c, where the hole is. The second situation we looked at was a jump discontinuity at c. So let's suppose we were taking a look at this function like this. So there's f right here. And let's suppose that the hole is at c, where this, let's give it some y value. Let's call it y there. And this right here, since it's closed here, this is equal to f of c. Let's go through the same thought process, same three questions here. Is f of c defined? And the answer is yes in this case, because we have a closed point at c. And that's up here at the second y value called f of c. So number 1, f of c is defined. It's equal to some real number. Okay, right up here it could be 10, it could be 6, I don't know what it is, but it is some real number at that closed point. The limit, however, fails to exist because the left and right hand limits are different. Okay, so let's take a look at that. What we're going to do is take a look at the limit from the left first. Okay, and as we go in from the left of c, the function's values are approaching y. So the left-hand limit is y, and the right-hand limit, as we come in from the right, the y values there are approaching f of c. So the right-hand limit is f of c, the left-hand limit is y. Those are obviously different, and because the left and right-hand limits are different, we say the limit does not exist. So the limit of f as x approaches c does not exist here. Okay, does not exist. Okay, that's a problem there, and the reason why is because you have a jump discontinuity there at c. And we found in the last section that whenever there's a jump at a point, there's not going to be a limit there because the left and right hand limits are different. Okay. The third situation that we looked at was this situation here. Okay, where you have a function f and it's got a hole at c, but it's also got a closed point right above c, and that's at f of c here. And let's say that this is some y value right here. Don't know what it is, but it's some y value. So we have a hole at c and a point right above it at c. Okay, and let's go through the same three questions. Okay, number one, is f of c defined? And the answer is yes in this case. It's equal to f of c. So f of c is defined. It's equal to a real number there. It's a real number. We can find it. And number two, does the limit exist? Let's find that out. Let's come in from the left. You'll notice that the y values here are approaching y, which is going to be our left-hand limit. We'll call it L. L is going to be our limit there. If we come in from the right, okay, the function values are decreasing, all right, to y, which is the same limit as the left-hand side. So in this case, the limit is L, or y, the first y value there in the graph. So in this case, the limit exists as x approaches c, okay, and it's equal to, in this case, it's equal to L, or y, okay? However, notice also that the limit is different than f of c. So on the third case here, in the third question, does the limit equal f of c? And the answer is yes in this case. The limit of the function, does not equal f of c, what am I saying? The limit as x approaches c, we found it to be L, but it's not equal to f of c. And the reason why is there because the hole's not filled. Okay? So we have to look at these graphs here and determine what does it take to be continuous. And remember, when I say continuous, I'm talking about the fact that you can take your pencil and trace the function without lifting your pencil on the function, or on the function as you trace it. If it's continuous, there would be no need to lift the pencil. You can trace it everywhere along the function. So what does it take? Well, in order for it to be continuous, there can't be holes. All right, and if there, what that means, or what that implies, is that f of c, in the first, look at the first graph here, f of c must be defined. Okay, in order for there not to be a hole or a jump, to make it continuous here, f of c must be defined. Okay, secondly, there can't be a jump. Okay, now to make sure that there's no jump, the limits on the left and right hand side have to be the same, which means the limit has to exist. Okay, and thirdly, even though the limit may exist, you got to make sure that the limit is equal to the function value at that point. It must be equal to f of c, otherwise there's going to be a hole in the graph. So basically we got to fill that hole on the third case here, and to do that we got to make the limit equal to f of c. So let's review. We need the function at c, or f of c, we need it to be defined so there's no hole. To make sure there's no jump, we need the limit to exist. Okay, so we need the function at c, or f of c, to be defined. We need the limit to exist so we can find it. And thirdly, we need the f of c to be equal to the limit. We need to fill that hole. So the limit of f as x approaches c must be equal to f of c in order to fill that hole, in order for it to be continuous. That's called a three-part continuity test, and let's write it down. Okay, so let's write down what we just said here. First of all, we need f of c to be defined. F of c must be defined. Let's just put it that way. That means that we're able to find it. We should be able to substitute c in the function and find out what f of c is. So basically it's a real number here, guys. That's what I'm saying. We need the limit to exist. Limit as x approaches c, okay, must exist, and we must be able to find it. Alright, and then we want these two things to be equal. We want the limit to be equal to f of c so that in case 3 the hole's filled, so there's no gap or no hole. We want it to be continuous. So we want the limit as x approaches c of the function to be equal to our function value in the first case here. We need it to be equal to f of c. This is called the three-part continuity test. Okay, it's a question on the exam. You guys are going to all have to state it all in English here, and then you're going to have to be able to apply it to many different types of functions. So commit it to memory. Alright, so let's go for it here. I made a little note about continuous functions here, so you should read it on your at your leisure here. It's a note on continuous functions. And when it comes to adding continuous functions, the result is continuous. That's one of them. Number 2, if you subtract continuous functions, it's continuous. And so on. So go ahead and read that through thoroughly and understand that about continuity here. Alright, and let's get into some examples here of how to determine continuity of the function at a particular point without looking at the graph. Okay, without looking at the graph. It's easy to determine continuity if you're looking at the graph. But if you don't, and if you don't want to graph it, then you have to come up with a test. And so what we're going to do is we're going to use that three-part test. Okay, so we have a bunch of examples here of piecewise functions, and we're going to test continuity at a particular point. In this case here, we're going to test continuity at x equals 1. So here's the process. The first thing we want to do is evaluate the function at c. In this case, c is 1. So we want to evaluate the function at 1. And then if you look at the function here, the domain of the function is all here. Okay. For the first part, your y could be equal to a linear function 3x minus y if x is not equal to 1, and y equals 2 if x is 1. Well, here your x value is 1, and that's right here. So when x is 1, y is 2. It's basically a point on the graph. So f of c is defined. Okay, first condition satisfied. The second condition is that you got to see if the limit exists. Okay, which means you got to take a look at the limit as x approaches 1 of the function. So that means you got to figure out what it is from the left and from the right, and your left and right hand limits. So the left hand limit as x approaches 1 from the left, that means you're coming in from the left of 1, which means you're not equal to 1, which means you got to evaluate that first part of the function here, your 3x minus 5. That happens by direct substitution there, so 3 times 1 is 3, minus 5, that's negative 2. Then you have to take a look at the right-hand limit, and that's x approaching 1 from the right. And if you're coming in from the right, you're definitely not equal to 1, so you got to evaluate that first part again. Alright, and do that by direct substitution here. And that's going to be 3 times 1, or 3, minus 5, and that's going to be negative 2. So notice here that both left and right hand limits are the same. So we say the limit as x approaches 1 of the function is equal to negative 2 in this case, and therefore it exists because we found it. Now notice that step 1 we got f of c was 2, and then the limit equals negative 2. Well, that means we're basically in this case right up here, this third case right here, where we have a hole and then a point above it, and we didn't fill the hole there. So what we have in this case is a line with a hole in it and a point 1, 2 above it. Okay, which means that in 3, the limit of the function as x approaches 1 does not equal f of 1. Because this is this right here is negative 2 and this is positive 2. They're obviously not equal. So condition 3 fails. So this fails, okay, not good, all right, and that implies discontinuity at 1. Discontinuous at x equals 1 because there's a hole there. Okay, hole at x equals 1. And that's what we're going to do for all of these graphs or all these functions here. We're going to do this 3-part test and check continuity at a particular point. So the next one here, we want to check continuity at -2. Alright, so what we want to do is, once again, we want part 1 here, we want to evaluate f of -2. Now, looking at the domain here, -2 is in that first domain, and -2 is less than or equal to -2, so you want to evaluate your first function there. So you want to take -2 and square it and then add 2 times -2. That's going to be 4 minus 4 or 0. So we got a real number there. It's defined. First condition satisfied. Number 2, you want to figure out the limit as it exists. So you want to figure out the limit from the left and from the right. So what do you do when you want to approach -2 from the left first? Okay, and then to do that, if you're left of 2, you're less than or equal to 2. So you're going to evaluate that left-hand side, or the first part of the function there. Do that by direct substitution. You're going to get -2 squared plus 2 times -2. We just did that earlier and we get 0. And then you want to evaluate the right-hand side limit. So approaching -2 from the right, that means you're greater than -2, and that's the second part of the function here. So we're going to evaluate our x cubed function minus 6x. I did that by direct substitution. -2 cubed minus 6 times -2. That's -8 plus 12, and that's 4. So notice that the left-hand limit is 0 and the right-hand limit is 4. So because of that, limit doesn't exist. So limit of the function as you approach -2 does not exist because the right-hand limits are different. That means you're discontinuous at x equals -2 because there's a jump there. Okay? So my end result, my conclusion is that there's a jump and it's discontinuous at x equals -2. Okay, now let's try it one more time here. We're going to check continuity at 0. So again, we need to evaluate f of 0 first. F of 0 is found by looking right here. When x is 0, y is 2. Okay, so we have f of 0 equals 2. Number 2, we got to figure out the function if it exists, or the limit, see if it exists as x approaches 0. So as x approaches 0 from the left, you're here. This is on the left, from the left, and this is from the right here. And we need to evaluate the x minus 6 divided by x minus 3. Do that by direct substitution. 0 minus 6 divided by 0 minus 3, and that's 2. And now we want to figure out the right-hand limit as we approach 0. That means we need to evaluate the root function. Okay, do that by direct substitution, and that's going to be equal to the square root of 4 plus 0 squared. And that's 2. Notice those limits are the same, which means the limit of the function is 2 as you approach 0. And notice in this case right here that the limit's 2 and f of 0 is 2. So they're the same. Conditions 1 and 2 are the same, and that's good. That tells me that the limit of the function as x approaches 0 equals f of 0. We just filled the hole there because the limit's equal to the function value, which means we filled the hole and we have continuity there. That's good. All right, and that means we're continuous at 0. Continuous at x equals 0. Alright, so there we had just an example there where we actually have a continuous function. Okay, next one here, we want to check continuity at x equals -1. So the first thing you do is you check you evaluate the function -1, and that's going to be equal to -1 squared plus 1 all divided by -1 cubed plus 1. That's going to be 2 divided by 0, and that's undefined. Well, that's no good because I said f of c has to be defined, okay, and here it's undefined. So already this fails to be continuous because you have an asymptote there. Contin US, okay. There's an asymptote. If you look at the graph, look at graph, and you'll see an asymptote at x equals -1, and that's why the function is not continuous there. Okay? All right. Next one is we want to figure out, see if the function is continuous at x equals 3. Okay, so if that's the case, we need to figure out what's f of 3, and you do that by looking here. F of 3 is equal to 9/2. All right, and then you need to figure out if the limit exists. So you're coming in from the left-hand limit and the right-hand limit are both going to be the same because you're going to both be evaluating this function here. So we need to evaluate the left-hand limit as you approach 3. And to do that, you're not equal to 3, obviously, because you're on the left, coming in from the left. So you analyze this first part of the function here. Same is true for the right, actually. And you're going to evaluate this. And what you're going to get by direct substitution is 27, 3 cubed is 27, minus 27, divided by 9 minus 9, that's 0. 9 minus 9, that is 0. Okay, so you got 0 divided by 0. That's indeterminate. We should probably factor this and simplify it to see what's going on so we can evaluate it. Let me see. Okay, so because this is an indeterminate form, because you can't divide by 0, so what you want to do here is you want to factor the function and simplify it in order to evaluate the limit. So let's do that. We are going to take a look at the numerator there, and we're going to factor it because it's the difference of cubes. And we're going to factor it as x minus 3 times x squared minus, plus 3x plus 9, all divided by x minus 3 times x plus 3. We're going to simplify it and remove the discontinuity there. We're going to remove the hole. This function has a hole in it. And so it has a hole at 3 and an asymptote at -3. And then we're going to evaluate the function by direct substitution here. So what is this equal to? It's equal to 3 squared plus 3 times 3 plus 9, all divided by 3 plus 3. That's 9 plus 9 plus 9 are 27 divided by 6. And that's equal to 9/2 when you're done. Now notice the limit's 9/2 on the left. It's going to be the same thing on the right because you're going to evaluate the same function. So the limit exists. Okay? I'm not going to repeat this for the right-hand side limit, but it's going to be the same, which means the limit exists, and that's good. So the limit at approaching 3 is going to be 9/2. And notice that it's the same of f of c here, or f of 3, which is also 9/2. So the limit of the function as x approaches 3 equals f of 3. We fill the hole there, and because of that, it's continuous at 3. Okay, continuous at x equals 3. Okay, so now what we need to do is apply our understanding of piecewise functions here and continuity to solve a problem like this. We want to, given a function here, we want to be able to find the value of c that makes the function continuous. Okay? And I'll tell you what, to avoid any confusion here, what I'm going to do is I'm going to change all my, well, no, that's fine. Find the value of c that make it continuous. And looking at the domain here, you'll notice that there's a switch in the function at 1. So the question is it continuous 1? What value of c, right here, what value of c will make it continuous at 1? Because the function changes from linear to quadratic at 1. Well, in order to make that happen, what we need to do is make sure that the limits from the left and from the right are the same. Otherwise, we have a jump there, which we don't want. So what's the right value of c that will make it continuous so that no jumps occur? So all we have to do for number 1 is evaluate the left-hand limit. So we need to take the limit from, as we approach 1 from the left, which means we evaluate the first part of the function here, your 2x plus c. And we want to make sure that's equal to the limit coming in from the right of 1. And if you're right of 1, you're greater than 1, so we got to evaluate the x squared plus 3, the second part of the function here. So this is on the left, this is from the left, this is from the right. Okay, both limits are found by direct substitution, so you just substitute the 1 in both functions here, and you're going to get 2 times 1 plus c is equal to 1 squared plus 3. That's 2 plus c equals 1 plus 3 or 4, so c has to be 2. Now, so in other words, if c is 2, then you have a two-piece function here that's continuous. If c is anything but 2, like 3 or 1.5, then there's going to be a gap at 1, or a jump, and it's not going to be continuous. So in this first case, c has to be 2. In the second case here, we want to take a look at what happens at 2, Look at from the left and also from the right. Okay, take a look at those limits. So what's the limit of the function as we approach 2 from the left? Okay, and that means you have to evaluate the first part of the function, cx plus 5. And we want to make sure that's the same as the limit approaching 2 from the right side. And if you're from the right of 2, you're greater than 2, which means you evaluate the second part of the function, your 7x minus c. Okay, we got to make sure that those limits are the same so there's no gap or jump there. So you'd find both by direct substitution. So you're going to have 2 times c plus 5, and that's got to be equal to 7 times 2 minus c. And that's 2c plus 5 is equal to 14 minus c. And then add c to both sides, you get c 3c, and then subtract 5, you get 9, so c has to be 3. So what you're going to do is to do that approach to all these problems here, and then no matter what the functions are, you're going to evaluate the left-hand and right-hand limits of all of them, go with the flow, and make sure that they're equal, and solve for that c. If you can't solve for c, then there is no value of c exists, then the function is not going to be continuous at that point. Okay? Okay, so go ahead and try those problems here. And lastly, what we need to do is check out what's called the intermediate value theorem here. All right. So the basic idea is this. So let me draw a graph here. All right. And suppose we have a continuous function. So let me change colors here. Suppose we have a continuous function here. Call it f of x. And let's suppose that this value is a, and over here this value is b. On the right, and you take a, substitute in the function, you get f of a. Take b, evaluate the function. All right, you got f of b here. And notice that if we have a continuous function here on a closed interval from a to b, this is called an interval. Okay, and we have some notation. It's called a closed interval from a to b. And we write it like this with closed brackets here, which is the same as this, a less than or equal to x less than or equal to b, which means x can be anything from a to b, including a and b. It's called a closed interval. So if we're working on a closed interval from a to b, looking at a continuous function, which means there's no holes, gaps, jumps, asymptotes, or anything like that on that closed interval from a to b, then the following is true. There exists at least, well, let me back up. If k, which is some y value, is between f of a and f of b, then there exists a c in the closed interval from a to b such that f of c equals that k. All right, what I mean by that is this. And if you go towards the function here and come down, there exists a c in between, or between a and b, all right, between a and b, or in the closed interval from a to b, such that f of c equals k. And notice this right here is equal to f of c. Okay, so let me repeat what I just said. If you have a continuous function, if f of x is continuous on AB, which is a closed interval from a to b, if f of x is continuous on a closed interval from a to b, and k is between f of a and f of b, then there exists, okay, a c in the closed interval from a to b, okay, such that f of c equals k. So when you take that f of the function, or c, evaluated the function, you get k. Okay, so now guys, just key on a couple important things here. I said there exists a c. Now when I say there exists a c, oh, you know what, I forgot a couple of key words here. There exists at least one c. Okay, at least one. Those words are important. I knew I forgot something there. That means that it may be one or more. So look out for that in your homework. There may be two values of c which make that happen, depending on the curve of the function. Okay, it may be something like this. Let me do something in green here. It may go up and down and then up again like this. This could be f, in which case, let's say that, let me switch, in this case, watch this, let's go red. There could be two c values right here. See, and we'll call that c1, that's c2. So there could be two c values, not just one, depending on the shape of the function here. So when I say there exists at least one c in AB, I mean one or more. Okay, just keep that in mind. All right, let's apply that here. We need to first check that k is between f of a and f of b, which means I got to evaluate the endpoints of the interval. These are called endpoints of the interval. I need to evaluate a at f, and then, or excuse me, f at a and then f of b, and then make sure k is in between those two. All right, so let's take a real problem here. Let's suppose we're working on this parabola here on the closed interval from a to 0 to 5. That's where a is 0 and b is 5. And we want to determine if there exists a c in that closed interval from 0 to 5 such that f of c equals 11, where k is 11 here. I have to check to see if 11 is between f of a and, or f of 0 and f of 5. Check to see if 11 here is between f of 0 and f of 5. So it means I got to do some evaluation here. So f of 0 is 0 squared plus 0 minus 1, negative 1. F of 5 is 5 squared plus 5 minus 1. And that's 25 plus 5 is 30 minus 1 is 29. And notice that 11 is between negative 1 and 29. That's obvious. Okay, so make sure you do that check here. Negative, you got to check to see if k is between those two values, and it obviously is. Let's go back to the theorem here. We have a continuous function. I know that that polynomial, that quadratic, is continuous because all polynomials are continuous. So that's checked. That's good. I checked to see if k is between f of a and f of b. That's good. That means the theorem implies that there exists a c, at least one of them, in that closed interval such that f of c equals k. Alright, so what I have to do is I have to check or find f of c, or set the function equal to 11 and find that value. So this is my step 1, and my step 2 is to solve for c now, okay, in 0, 5. It has to be a value in that closed interval. So I set the function value equal to 11, or the function equal to 11, okay, and solve that equation there. So I'm going to set it equal to 0, subtract 11, so I get x squared plus x, negative 1 minus 11 is negative 12. I'm going to factor it. And notice that x could be equal to negative 4 or positive 3. Now, negative 4 is not in 0, 5. Negative 4 is not in the closed interval from 0 to 5. Alright, but 3 is. Okay, 3 is in 0, 5, which implies that c equals 3. Remember, c has to be in that closed interval. So the first thing, let's review what I just said in its entirety here. So let's look at the whole problem here. We need to check to see if it's continuous. And I said it, but I didn't write it down. Since all polynomials are continuous, okay, the first thing is satisfied. The first part of the theorem is satisfied. F has to be continuous. Second part of the theorem is that I have to check to see if k, this is your k, which is 11, is between f of 0 and f of 5, where a is 0 and b is 5. So I evaluate the function at 0, I get negative 1. Evaluate the function at 5, I get 29. 11 is between negative 1 and 29. So the second part of the theorem is satisfied. And that means there exists a c. And if it exists, that means we can find it. So I set my function equal to 11 and solve that equation. So when I do that, I solve the quadratic, I factor it, use my algebra 2 skills, and I get two solutions, negative 4 and 3. And then you got to check to see which one's in the closed interval from 0 to 5. Negative 4 is outside the interval, and 3 is inside the interval, so c must be 3. And that's how you use the intermediate value theorem, abbreviated IVT. Intermediate value theorem. All right, there's a couple problems on your homework, problems number 85 and 86 that you have to try. So give this a shot and come to prayer tomorrow, and you can ask me questions when I see you in class. Good luck.